What am I saying? Sorry. Yeah. Maybe. Did everyone have a good holiday? Maybe. Hopefully, y'all had some time to rest, or maybe mug. I don't know. Oh, that's nice. That's nice, Michelle. Today. What did I do today? Today was just I had regular school, so it was just lectures and stuff, going through papers, exams. I have A level Chinese next Monday, guys. Please pray for me. Ah, thank you. Wait, by the way, sorry, I would have wanted to do another emath lecture this or next week, but this week, like maybe Wednesday or Thursday, but I don't think I'll have time. So sorry about that. I'm considering maybe an emath lecture potentially if that's a possible thing y'all want. But yeah, for emath will be a bit tight, so probably not. Oh, which JC am I in? I'm in Eunoia JC. Yeah, very fun, very fun. I'm J1 by the way, so like it's very chill. I like Eunoia. Come to the Eunoia guys. Shameless plug. Yeah. Yeah, thank you. I agree. EJC is really cool. I made a lot of very cool friends here. The vibe is very fun. If you have any questions about anything, if you have any questions about the lecture or anything in the middle of the meeting, just feel free to send in chat. I'll try to address it. Yeah. Eight, 10. A math same as H1 in JC. Okay, the interesting thing about H1 math in JC is that it is quite similar. Okay. Math generally we have two sides. Pure math. So pure math is all like the algebra, a lot of that stuff. And then there's also probability and statistics, which is as it is probability and statistics. For H1 math, the pure math side, it's pretty much what you learn in A math. It's like exponentials, logs, logarithms, like graphs, differentiation, differentiation integration, but a lot of stuff is omitted. Like for example, right, fun fact, guys, they don't touch trigo at all in H1 math. Product rule, quotient rule for differentiation also, they don't touch at all in H1 math, interestingly. But probability and statistics, that's where all the new stuff comes in. So that's the main bulk of H1 math. Between H1 math and H2 math, the probability and statistics portion is pretty much the same. So if your pure math isn't very strong, if your pure math is good, but your probability and statistics are not as good, try to go for H2 math because you can get more marks that way. Calculus, yeah, calculus. So like, yeah, pretty much. I mean, differentiation integration. I forgot if there's tangents in there or rate of change. I know area under a curve there is. Yeah. Okay. 8:10. I guess we can start. Are you all ready? Everything okay? Okay, dokie. Let's go. So the notes are all here. Sorry, it's a bit rabak. It's a bit all over the place. I was trying to figure out a way to squeeze it all. But yeah. So quad jump and vectors. The reason why I decided to do a lecture with like these two, right, is because usually a lot of emath questions will have questions. A lot of emath questions will combine these two topics together. So like lots of questions like to combine questions like to combine. So it's just a general thing that I've noticed in the TOISs, they really like to combine these topics. And they are quite linked. Like you can see later in the lecture, I'll try to explain. But if you think about vectors and quad geom from like a similar perspective, they are pretty much very, very similar. There's a lot of overlap basically. So yeah, okay. So we start with coordinates, the entire basis of how quad geom works. So and in coordinates we have our xy system, so x y. So like these coordinates, right? How we how we look at the coordinates, right, is we have our x-axis, y-axis, and our origin. So the origin is very important because basically what this xy tells us is the x will tell us how many steps to move left or right, and the y will tell us how much to move up or down. So example, if you look at 5 3, right, this pink coordinate over here, basically what they're doing is from here to from the left they go 5 units, and then they go up 3 units. So that's how you interpret coordinates. I know it's a bit sometimes you have to look at it in a bit of a geometrical way, but if you look at it from this kind of horizontal distance first, then vertical distance, it becomes a lot easier to visualize. Then the thing you have to remember about coordinates also is that negatives will play a big part. So usually positive values will take it to be moving right, will move it right and up. So these are like the kind of positive directions if you think about it. So negative means we'll just move the opposite direction. So a negative x coordinate is like -1. We will go left by 1 unit. So we'll just do this as -1, and then -2 for the y coordinates, which means we go down. So yeah, generally when you think of coordinates, we try to think of it this way. Okay, gradients of lines. So hopefully y'all are aware of the formula. So m represents gradient, right? If let's say we have two points, x1, x2, x1, y1, and x2, y2, which are points on the line that we are trying to find the gradient of. Uh, what we do is we can do y2 minus y1 over x2 minus x1. So this is the general equation of how we find the gradient. Okay. I thought I have a diagram for this. Okay, it's fine. So, yeah. How we interpret this, I thought I had a diagram for this, sorry guys, but yeah, okay. So if you draw like a line out, right? Okay, wait, actually I can use this, I'll use this one. Okay. So we have our two different points. We have our 1 3 and our 7 7 over here. So how you interpret the gradient is we use every teacher will always talk about this rise over run, right? I'll write that down later, rise over run. So which means from this point all the way to this point, how much does the y increase for every unit x increase? I know that's a bit abstract, but pretty much it's saying, okay, so from this point to this point, we calculate the x movement. So from, you see the x coordinate goes from 1 to 7, which means you can do the math. It goes goes to the right 6 units, and then it goes up by 4 units. So if we wanted to find the gradient, you can say, okay, m equals to 7 minus 3. So that's, we can take this is our y2, this is our y1, and then which will end up with 4. And then our x2 minus x1, 7 minus 1, which is our horizontal distance traveled, and you end up with 4 6, which is a gradient of 2/3. So essentially, what this 2/3 tells you is that if I move in the x direction, if I move to the right by 1 unit, how much does it increase vertically? So yeah, if you look at the formula, you can actually think about how the order of the points doesn't matter. Like you can have y1 minus y2 over x1 minus x2, and it's perfectly fine because it's essentially as if you're like just taking the negative of both sides of top and bottom, so it will just cancel out. So that's perfectly fine as long as you pick any 2 points that are on the line, or like you have any of the 2 points that are on the line. You can find the gradient with just 2 points. Okay. I'll erase this real quick. Okay, so these are a few interpretations of gradient, because we'll talk about line equations later on, but these are very fast ways to immediately tell how might the line look like. So like we said, right, the gradient, you think about it as like for 1 unit moved in the positive x direction, how much does it move in the y direction? So if we look over to this graph over here, so we can notice that as x increases, right, y is also increasing, which means for you take one step, basically y is increasing, which means y will have a positive, the gradient has a positive value. So we say m is more than 0. So any sort of line you have that with the gradient being positive, you just interpret it as an increasing line. Then vice versa for decreasing lines, it's less than 0. Because your rise over run, your run will always be, okay, not always, but when you think about the definition of the gradient, right, you're moving in the positive x direction, it's to the right. So if your gradient is negative, it means your quote unquote your rise is negative. So y is decreasing essentially. So yeah, less than 0. If you look at this horizontal line where your x, you go on like forever and ever and ever and ever, but your y just doesn't change. It doesn't increase, doesn't decrease, it stays the same. Your rise is 0. Hence your rise over run, your gradient is also 0. So interpret it as m is 0. For vertical lines, this one is a bit of a tricky one, and a lot of people will tend to misunderstand or like mix up between horizontal and vertical lines. For you think about it, right? This vertical line is a vertical line. The x doesn't move at all, actually. So your run is 0. So your m will end up with like don't know what over 0. But as your teachers might have told you, you cannot divide by 0 because that gives you an undefined value. And if you think about it also, you can't really tell how much y is increasing. It could be going this much, I don't know, this much. So for usually we just say m is undefined. We have an undefined gradient. Vertical lines, they will always have an undefined gradient, no matter what. Okay. So that's pretty much it for gradients. For the length of the line segment, so okay, there's kind of a slight difference between using the words line and line segment. Line essentially, what my teachers told me was that a line means something that goes on forever and ever and ever. So like there's no endpoints. A line segment means like there's endpoints. So it like maybe the endpoints are like here and here. These two, like these two, and yeah. So this is considered a segment of a line. So if you go down, let's go back down here, right? We want to find essentially this distance. And if you draw out this diagram, you realize, right, because x and y axis are perpendicular, so these two lines are perpendicular. We found out that this is 4. We found out this is 6. So when you have the two sides of a right angled triangle, we can very easily just do Pythagoras' theorem. So that's what I have over here. This formula we are going to derive comes from Pythagoras' theorem. So I know that I had friends that like try to brute force memorize this formula, but they don't realize that actually it's basically just Pythagoras theorem essentially. So like if let's say you can say pretty much like let's say the d is our length of the line segment, so d squared will be equal to 4 d squared equals to 4 squared plus 6 squared. So you can just square root both sides. D equals to square root 4 squared plus 6 squared. Yeah. Normally, yes, when we square root both sides, you have to consider positive and negative. But in this case, distance, length, we know definitely has to be positive. We can't have negative distance. So that's essentially what we're gonna do. So same thing as just now. X1 and x1, y1, x2, y2. They are the coordinates of the endpoints of the line segment. So we could take these as our endpoints. The formula will always be given as x1 or x2 lah. Okay, for consistency, x2 minus I can't write x2 minus x1 squared plus y2 minus y1 squared. So if you try to think about the formula, you will see that it's pretty much always the same. Every single line segment you draw, you can always Pythagoras it out. Okay, let's briefly discuss line equations. I think I've missed out that part. Oops, sorry guys. Ah, okay, we just read for this. So the typical line equation we have is y equals mx plus c. So we are all very familiar with this line, hopefully the line equation. Hopefully, as we know, uh, as x increases, y will increase by a certain amount, that's how we define the gradient, right? When x increases by 1 unit, how much does y increase? So this m over here, this is our gradient. This c is basically our y-intercept. Because think about it. Let's draw out a diagram here. Line. Let's say this is y equals to 3x plus 3. Okay, a bit. Wait, okay, 3x plus 2. It's not very proportional, but yeah, don't worry. The y-intercept will essentially be this point over here where it cuts the y-axis. And you realize when it cuts the y-axis, x equals to 0. So if you sub x equals 0 into here, you just end up with y equals to 2. Which means this is 0, 2. So no matter what your gradient is, you can change the gradient as much as you want. The y-intercept will always stay the same. So this is why people will call this line equation the gradient intercept form. I think that's correct. Gradient intercept form of a line equation. Yeah, of line equation. Technically, you can express lines in any way. So, for example, let's say you wanted to say like 2. Sorry, this thing is very finicky. I don't know why it's doing this. 2x plus 3y. Oh my god, 2x plus 3y equals to 5. So it's not in the y equals mx plus c form, but it is still a line equation. You can just shift things around. So, so 2x plus 3y equals 5. You can shift things by saying, okay, let's set 3y equals to minus 2x plus 5. And then you just divide 3 all throughout. And you will end up with your gradient intercept form. But yeah, just remember that when you want to find gradient or y-intercept or stuff like that, right? Try to make sure that your thing is in this form first, so that the computation will be easier that way. Okay, for finding line equations, there's usually two methods. Okay, wait, two methods to find line equation. Two methods to find line equation. Typically, they will give you information to help you find the line. Okay, so I think usually, let's say they give you the gradient. Hold on, gradient is -1, y, okay, no, and a point on the line. So it can be any point on the line. Let's say 2, 3, right? So the first method we have is we just sub it into y equals mx plus c. Y equals mx plus c. So we know our gradient, our m is equal to -1. Our x and y, they are basically 2 points that x and y are just 2 values of the coordinate that lies on the line. It can be literally any coordinate and it will fulfill the equation. So we can just sub anything in. Since they give us 2, 3, we can just say, okay, y equals to 3 equals to -2 plus c. And so c is an unknown here. We're trying to find it. So what we can do is just shift things around. We end up with c equals 5. So we end up with our final equation. Y equals to our m is -1, as we said before, plus 5. So this is the first method you can do. Second method, I'm not as sure whether this is technically given in the emath thing. I know, okay, emath, they like to use this a lot, but I'm pretty sure emath, it should be okay because it's a valid method. Yeah. 2. Method number 2, right. So we know that m equals to y2 minus y1 over x2 minus x1. So let's change this up a little bit. We'll say that y2 and x2 are literally any points on the line. And we can multiply both sides by this denominator over here. Wow, this laser thing is really annoying. We can multiply and we end up with y minus y1 equals to m multiplied by x minus x1. So emath people, if you recognize this formula, this is how it's derived. So y1, y minus y1 equals mx minus x1. We'll do the exact same thing where we just substitute all the values that we got. So, okay, y minus, the y1 and x1 will be the points of our coordinates that are on the line. So again, y1 equals to 3 equals to m is -1, x minus 2. And then you realize if we shuffle things around, we once again we get y equals minus x plus 5. The good thing about this method over here is that you don't actually need to bother finding this unknown c, which can be convenient under certain circumstances. It's really up to your personal preference which one you want to use. Personally, I prefer second, but yeah, again, it's really up to you lah. Just shift this down a little. Okay. So I'll label a quick note right over here. Pencil's not working. Sorry guys, my PLD is a little old. It's been surviving for like 5 years, so I'm gonna have to try to, yeah. Must find C. No need find C. Convenient, yay. For now, are there any questions? Am I going too fast? I think I'm going a bit fast because of the time limits like stressing me out. I don't want to like end up like getting cut off in the middle of the meet. But yeah, is everyone okay? What's C? Okay, so yeah, C is basically what we said is our y-intercept. So it's our y-intercept will always have this form of it. It will be at on the y-axis, any single point on the y-axis, x will be equal to 0. So we have that, and C is basically the y-intercept, correct. So these are the coordinates of your y-intercept essentially, because how lines, what we can do with the lines is when x equals 0, when x equals 0, we sub it into the equation over here, and you end up with your y equals to, this thing becomes 0 because your m equals 0, and then plus c. So essentially, when x equals 0, your y will be your c value, which is, yes, as Arvin says, an unknown number that you need to find. Yes. Okay, Ken. Any more questions? Everyone doing all right? Nobody dead, hopefully. Okay, cool. I just have this like one little tidbit over here because it's a word I learned in JC that you don't need this. You definitely don't need to know this. It's just like a fun thing. Like, you know, if you ever go to math websites, you see like this word, maybe you know. So we talk about how, you know, points that are on the line, blah, 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 blah. What we essentially mean by that is any point, let's say this equation, right? Okay, wait, let's go to our minus x plus 5 example. Zoom in, zoom in, zoom in. Okay, any x, okay. Bro, okay, this sucks. Any xy coordinates we have, if they lie on the line, it means if I sub this x and y into the equation, it should be correct, right? So some certain, if I, let's say I have, okay, I can have things like maybe 2, 3, that's a line we knew, a point we knew is on the line. We can have something like 5, 0, 5, 0. Because you realize you sub x equals 5, y equals 0, the equation is 0 equals 0. That's true, which means these points are, they belong on the line, they fulfill the equation, this sort of thing we call criteria. So a collection of points of that satisfy these conditions, right? So let's say the condition is y equals minus x plus 5. And this quote-unquote collection of points is the line that we draw. Because this line connects every single possible point that fits the equation. This collection of points, in very formal atas math terms, we call this a locus, or plural form will be loci. So you can look at these two examples over here. The locus of y equals x plus 1, it will just be this long stretching line that passes through every single point, every single coordinate that has x and y that fits this criteria. And locus of going up a little bit, up a level, y equals minus x squared. It's the shape of the locus is a upside down parabola. Okay, not really upside down, just a frowny shape. So again, not necessarily just a little fun thing. Hopefully, yeah, I don't know why they need to give such an atas term for this kind of concept. But yeah, okay, that's pretty much quad geom done. Let me just check how much time I have left. I don't think I can check. Oops. Sorry. Do you all know how much time I have? 28 minutes. Okay, 20 minutes. Let's push this out. I think it's possible. Okay, so that's pretty much it for quad geom, if I remember correctly. Now we're on to vectors. Vectors is one of the biggest killers I've seen. I'm pretty sure the reason why the poll for quad geom and vectors, the reason why quad geoms and vectors won, it was not because of the quad geom, it was because of the vectors. Because it is the last topic you learn in Sec 4, and it is a bit of a killer because it feels so abstract, right? But it's, if you think about it from a coordinate geometry lens, it quite helps. So, okay, let's go. A vector, basically the definition of how we defined it is something that has both magnitude and direction. So magnitude is basically just like a certain, it goes a certain distance, and direction is direction. These 2 points will be quite, they'll come out in trying to explain a certain phenomenon with the vectors, so don't worry too much about it. First and foremost, we need to talk about proper notation, because a lot of people will always have issues with their notation. So let's say you have this vector over here. Sorry, I forgot to draw the arrow. Okay, arrow. People will forget that vectors, you cannot simply say like, oh, OA, right? If you want to talk about the line OA, that's fine. But if you want to talk about vectors, you need to specifically have the arrow on top. Please remember the arrow. It's very easy to forget. But yeah. And sometimes we can refer to this vector as, for short form, we say A. But you have to remember the squiggly line, or what we call a tilde. It's, yeah, vector notation is a bit annoying, but a lot of people will forget, and a lot of people will lose marks because of this. So please remember to have formal, proper notation so that you won't lose marks. Yeah. The third way to express vectors is do a column vector, which basically means yeah, you express your stuff in a column. We explain what this is in a bit, but yeah, so these are the 3 ways to have your vectors expressed. Okay, position vectors. So you will hear the word position vector thrown down a lot. Like sometimes the questions will ask you, oh, find the position vector of point A, for example. So you need to kind of understand what this means. It's pretty direct to understand. Basically, a position vector is, if you can read here, a vector that indicates the position of a point relative to a fixed point. Typically take this fixed point to be origin O. So let's say we have our position our O over here. And then we have our point with coordinates 2, 3. Sorry, this is looking very blurry. Let me just fix this. 2, 3, right? Remember how we talked about coordinates, right? The way we thought about them. The first coordinate tells us how much to move left or right. So in this case, we moved left 2 units. And the y coordinate tells us how much we move in the y direction. So in this case, 3 units. Why did I draw that? I didn't need to draw that arrow. Okay, 2 units, 3 units. So we would define this as the position vector. So this is how we find the position vector. So the position vector is basically our coordinates. It's basically your coordinates. We literally just like put stuff your coordinates into the bracket, and that is your position vector. So what this essentially says is from our position, our O, our origin, our starting point, how much the first, this sort of what we call an element, is how much we move horizontally. The second element is how much we move vertically. So it's again pretty much exactly the same as coordinates. So we look at this other example over here. Again, negative values will matter. So if we move to the left instead of the right, the left means that the number will be negative. So in this case, the position factor we are having is -6, sorry. So we move -6 units. And then we move down instead of up. So down is a negative position direction, -2 units. And this gives us our point -6, -2. So again, coordinates and position vectors, it's pretty much the same because everything we're doing relates back to the origin. The origin is always where we start. So yeah, and then vectors have that whole thing about the direction, everything, right? Because again, it gives us, we can essentially split the vector into these two different parts. So the horizontal part and the vertical part. Technically, there's a word for it. It's called like resolving the vector, but again, that's just a way to understand vectors. Okay. Let's go to this one. Okay, adding and subtracting vectors. This one also a bit annoying sometimes, but don't worry, we'll get it done. So when, let's say you have two vectors, right? Because a vector is sort of like just a movement in a certain direction. So let's say I move in this direction, and then I move in this direction, I move in this direction, I move in this direction. So the total distance I traveled is the sum of all these arrows. But essentially, the only real net movement I made is just across this entire thing. So from the start to the end, I pretty much just traveled this dotted line. So yeah, this kind of thing we do is called adding vectors. We add vectors to find the resultant position where we end up at. So if you want to add vectors, there's this thing we have to remember called the tip to tail method, where again, we will usually represent vectors as an arrow. Oh, by the way, your arrows, whether you do it like this or like this, I don't think it makes a big difference as long as it's understandable. But yeah, basically, we'll start from the tail of the vector, go up to the tip. The tail of the vector go up to the tip. From this tip, we have to continue on, attach a tail to it, and move like that. So it's tip to tail, right? Connecting all the tips and all the tails, and this is how we move. So if you have these two vectors, let's say A and B, oh my god, this blurriness. A, B. The arrows are, you can see their tails are the ones that are connected. It's tail to tail, but we cannot add vectors when they're tail to tail. So what this diagram kind of does is, you imagine, right, you shift this B vector up over here. So this is basically our B. And you can notice that this kind of draws out a parallelogram, right? These two B vectors are the exact same. They're the same magnitude, same direction. And once you connect the tip to tail, you find out the final movement you make is this vector from O to C. So if you want to describe the vector O to C, we can say that OC is equal to A plus B. Because yeah, you moved in the direction of A, and then you moved to the direction of B, and you ended up at C. So that's how we interpret vector. Oh my days, that's how we interpret vector addition. Then you can also express it as OA plus. You can say OA plus OB, but if you want to draw it out like this, we can basically say it's OA plus AC. So this is kind of what we think about the tip to tail, right? O is your tail, and then A is your tip. When you add a vector, the next one, your A becomes your tail. So these two have to be when you add vectors, these two have to be the same. So wait, same. And your N vector becomes the tip. So you always have to remember this. You have to start with a tail, go to a tip, tail tip, tail tip, tail tip until you reach a tip. Then we go on to vector subtraction, which is a little bit weird. Okay. let's say we have our OA and OB. What if you want to find the vector from here to here? So this will be denoted as AB, right? Remember your arrow. From point A to point B, what is the vector that like brings that there? If you try to think about this in a certain, okay, wait, yeah, for this we need to talk about this scalar multiples. So there's this whole thing over here. So we just fill in like a scalar multiple is basically when you have a vector A and you multiply it with some constant, some real number. This K, we call it a scalar because if you look at it this way, right? A, let's say A goes like that. 2A is basically just A and another A, two A's put together. So a scalar multiple, the scalar, you think about it as a number that scales your vector. Yeah, pretty cheap, but scalar multiple of A. The interesting thing is, okay, when you multiply by a number, it changes the magnitude. So that's pretty much, it either makes it longer, shorter. When you add a negative to it, that's when the things change. Because when you add a negative to it, what happens is that your vector flips position, flips direction. So at first it's going this way, right? When you add negative to it, it goes in the directly opposite direction. So yeah, basically that's how we define parallel vectors. So if you can represent some vector b as a scalar multiple of a, it basically means b is either a scaled version or a flipped version of a, which means they are parallel. They're definitely parallel because there's no other changes, no turning, no whatever. And that would be quite useful for vector subtraction because over here you realize, so when we have like vectors like this, right? If you look at the OC example, it's basically the path from O to C. We can go literally any route we want. We can go from O to A. We can run A to B, B to some other point, B here, there, but back up here. As long as the start is at O and the end is at C. So A, B. One possible route is we can start from A, we can actually go backwards here in the opposite direction of the A vector and then continue along the direction of B. And that gives us our AB. So when you write this down, you are going in the opposite direction of A, right? So that would be negative A. And then we continue on in the direction of B plus B. So that's, if you move it in this way, okay. So OA is from the A vector from O to A. If you move backwards, it's from A to O. So we'll flip it like that, and then plus OB, because that's our B direction. So again, this is pretty much a tip to tail, except that a way to think about this is, oops, okay. A way to think about it is, my teacher taught me this method called the n minus start method. So it's like, it's kind of a mini shortcut if you don't want to like try to visualize like, oh, okay, I go this direction, then I go that direction. Essentially, think about position vectors, right? Your B n minus start, so the position vector of B minus position vector of A, the start. So n minus start. Yeah, so this is quite important. Negative OA is this is just AO. That's why how we end up with AO plus OB. Technically, you can flip the order of these. Like you can do OB plus AO. That doesn't really matter. But yeah, this just kind of helps with the visualization of how vectors move. Collinearity is another application of parallel vectors. I guess you can call it that. Basically, when we talk about collinearity, because questions will sometimes ask about, oh, are the points collinear or not? 3 points, they are collinear if they are lying on a straight line, on the same straight line. The same straight line. This is how we define collinearity. Oh, I forgot a line here. Straight line. So as you can see, right, A, B, and C, they all lie on this line, but we can't really say that for sure because I mean, I don't know, maybe the vectors, the coordinates are just weird. So in terms of vectors, how do we show that 3 points are collinear? So it will really come down to this key method, which is to show that any two of these vectors are parallel. So it can be like, if AB and BC are parallel, that means this entire thing is parallel. But okay, you have to remember, when you pick your 3 points, right? You yeah, so the key idea is that your vectors, they will share a common point. So okay, let's say A, AB, and AC. If they are parallel, it essentially means that, like AB. Okay, it's quite a logical leap lah. So it's A to B is parallel to A to C. It's basically the exact same direction. It means it's on lines on the exact same line, just one direction go through. Sorry. Got 15 more minutes. Okay, Ken, thank you. I will try my best. Yeah, I don't have much else. After this, should be quite fast. Yeah, collinearity, that's pretty much that's it. One key question that they like to ask in vectors is write down 2 facts about these 3 points. This is a bit of a weird question. I don't like when math they ask these kind of explanation questions because I just want to do the math itself, but not to worry. So when they ask about 2 facts, they are usually expect translation vector. Okay, I finish this first, then I'll talk about translation factor. Okay, can. Uh, so when they want to ask 2 facts about 3 points, typically they are asking. Usually the points will be collinear. That's what something they will ask you to find. They are collinear, so you just have to do that thing that we did over there. The second fact will have to be usually what they're looking for is ratio of lengths. So let's say maybe they could ask, oh, okay, A, B, and C are collinear, and let's say AB equals to AC. So that's a ratio of lengths, how the lengths are relative to each other. You can say like AB, okay, no, AC equals to 2AB, something like that compares their lengths essentially. So you cannot really say for your 2 facts, you cannot have one is collinear, one is AB parallel to AC, because they basically mean the same thing. Because AB parallel to AC, that's how you found out that they were collinear in the first place. Okay, translation vector. Right. That's kind of I think I know what you mean. Translation vector. The word translation basically means the movement of something. Like you move a certain thing in a certain direction. So, okay, we think about our origin O, right? Our 0, 0. Translation vector means, I'll use a different phrasing for this part. We translate this 2 units to the right, 3 units up. So our quote unquote translation vector is this column vector 2, 3. Because that explains movement. The 2, 3 shows us movement. How much movement we go in the X direction, how much movement we go in the Y direction. Transition, like I'm pretty sure that's what a transition vector is. I don't really see that term a lot, but I'm guessing that's what this is referring to. So vectors, if you think about that in that way, it translates a point, it moves a point. So like from this point to this point, how do I move in order to get there? Yeah, does that answer your question, hopefully? Yeah, pretty much. So a translation vector, yes, it can be from any point to any point, and then we just move. The good thing about position vectors is basically it's like a translation vector, just that we start from the origin. Yeah, can. Okay, I saw a heart reaction. That's good. Okay, length of a vector. We will position vectors like the normal coordinate system. Yeah, pretty much. That's yeah. Okay, length of a vector. I should probably speed up a little bit. I think I'm running out of time. Length of a vector, let's say A and B have position, oh my god, this wording is wrong. Have coordinates. Sorry, mistake. I was like rushing through this notes last minute. Coordinates, we go x1, y1, x2, y2 again. So length of vector, or sometimes they'll call it the magnitude of a vector, we'll draw like these 2 vertical lines around the vector that we're trying to find. You think about it in a certain way, right? A to B, if we go back to this diagram once again, we can basically say this is our A, this is our B. From A to B, the vector goes 1, 3, and from 0 to A is 1, 3. From O to B, the position vector is 7, 7. Okay, so if you kind of think about it, the AB will end up with this the vector subtraction thing again, and sorry, I'm a bit panicking and running out of time. Yeah, magnitude of vectors is essentially just the exact same as how we find the length of a line segment. It's the exact same uh, formula. Because, thank you, I'll try. uh, yes. So, if you want to find, like, let's say AB, the vector AB, from okay, to find the vector AB, we move from A to O, that's -1 units, because we started from 1 to go to 0, that's -1. Add 7 units to end up at B, that's 6 units in the x direction total. So again, 6. And then Y, you would use the same logic for. So again, exact same logic. So yeah, pretty much. Everything is linked to Pythagoras theorem. Everything is linked to the, yeah, because the way we define the vectors, right, is how much you move vertically, how much you move horizontally. It's still a right angle, so you can Pythagoras everything out, basically. Okay, well, I've seen the chat right now. Thanks, guys. Thanks, guys. Oh, I realized this is the first time anyone's like hearing my voice. So, haha. Magnitude. Okay, the thing you have to realize about magnitude is you can't really split the magnitude in this way. Like over here, you can't split it this way. The only way you can split it is when A and B are parallel. They like line up exactly. So that you can do it like that. But if let's say your A vector and B vector are connected like this, and your A plus B, the net movement is like that, definitely this length is a lot less than the sum of this and this length. So like that. Technically, there is a name for this. It's called the triangle inequality, where they say like, oh, like A plus B is less than or equal to A plus B. But you don't need to know this. It's just thing you can look up. Triangle inequality, because like lengths of a triangle. Yes. Gradient of vector. Yeah, again, same thing. Rise over run. You think of your vector like a line segment. So your vector, let's say this vector is 3, 4. Because you moved in this direction 3 units, you moved in this direction 4 units. So rise over run, 4 over 3. So yeah, basically what Irvin says in the comments. Thank you. Okay, area ratio questions. They like to always ask these questions about like, oh, what's the ratio of the areas of the triangles, right? Different routes you can take. You will really have to logic out this one. It's a bit difficult to strict rote memory, try to apply. So you really have to look at the context. One way you can do it is similar triangles, where okay, area of ABC equals over area of ADE. These two are very similar triangles. You can tell. You can use your AA or your whatever to prove it. But yeah. You can say, let's say BC equals to DE squared. This is like your rules of similarity, right? How to find the ratios and everything. In terms of vectors, what we will do is BC, the magnitude of the BC vector over the magnitude of the DE vector, then this squared. Usually they will give you a way to find these ratios, but yes. The other way they like to ask us is when the triangles have the same height or the same base length. So let's say ABC and ABD, ABC, ABD, they have the same height, which is this AX. So you can find the areas individually. So half times ABC, right? So ABC times BC times AX over ABD, half times BD times AX. And you realize that these everything will cancel out. And you can very neatly have BC over BD, like that. So again, you really have to use logic to try to understand the diagram, because every diagram will be different, definitely. So you have to try to look at the problem at hand and try to find a way to work this out. Yeah, so the good thing about column vectors is that they are position vectors. Sorry, I write position vectors. Because position vectors, you realize we take it from the origin, So one of the endpoints on the origin, and if you sub that into our very nice formula over here, your x1 0, your y1 0, it's laggy. You can pretty much just say that the length is just a squared plus b squared. So hopefully you all understand that like you can just sub 0, 0 and that works. Okay, last one. Important things to note. So sometimes vectors, they confuse it with certain topics. So example, polygons. Polygons, you know, they have like certain features. For example, equal sides or parallel sides. So let's say we have this very nice regular hexagon over here, a bit, okay, not very nice, but um, you realize, right? Opposite, every side is the same magnitude, and the opposite sides will be parallel. So if you put this into vector terms, you can say AB, the vector AB equals to the vector ED, because you realize A to B, E to D, exact same magnitude, same direction. That's why I mentioned when you deal with vectors, magnitude and direction always come in handy, because it explains literally everything. So similar logic, you can say FA equals DC and EF equals to CB. Then for things like trapeziums, right? Okay, magnitude, you don't really know for sure that they're equal, but you know that A, B, and CD are definitely parallel. So what you can say is AB equals to KCD. It's the whole thing about parallel and scalar multiples again, right? When you just take the vector, multiply it with a scalar value, and it's, so that's how you show that they're parallel. Okay, another way that they like to, wait, sorry guys, how much time do I have left? Okay, I'll quickly explain first. The other topic they like to fuse this with is simultaneous equations. 3 minutes, okay, that's perfectly fine. Let's say they give you end up, maybe you do workings and you end up something like this, and you need to find P and Q. So you realize, right, you can split it into A and your B, and then on the other side, your A and your B. What you can do is we do this comparing coefficients of A and B. So we compare like the numbers we attach to A and B. So we compare the things attached to A. So this P plus 1 at the start, and then this 2Q. So 2Q. And then we can compare the B. So P plus 2Q and negative 3. Negative, you must remember that it's there. P plus 2Q equals to negative 3. If you shift things around, I forgot what exactly you get, but you know how to solve simultaneous equations, so that's it. Same thing when you have column vectors. Sorry, this is wrong again. I forgot to update this. Compare, let's say elements, right? Because yeah, that's usually what we call these. The top and the top will have to be the same, and the bottom have to also be the same, because they can't really, they have to be the same. If not, they're not the same vector. So x plus y equals to minus 3x plus 1, minus 2x minus y plus 4 equals to 7. So you can reshuffle this again. You end up with 4x plus y equals to 1. Let's just shift this. 2x plus y equals to minus 3. And then again, you can solve the simultaneous equation just like that, and then you'll end up with x and y. So this is just a general guide for vectors and quad geom. I tried to throw in a few tips to hopefully help, but yeah, this is pretty much it. If you have any questions, I'm so sorry, we're running out of time, so I can't do this. If you need any questions, you can ask in either the Magas chat or like my own channel. Yeah, shameless plug, join my channel, please. But yes, that's pretty much it. Any questions, you can just throw. I will answer as quick as I can. I will send this annotated notes later on. But yeah. Okay, done. Thank you guys. Hope this was an okay lecture. I was a bit nervous, but yeah, my apologies. Thank you so much. Okay. No worries, gang. Thank you. Thank you. Wow, I feel so supported, gang. Wow, this is nervous. I've never done this before. Okay. Yay. Thanks, guys. Ask questions either in the Magas Telegram channel in the comments, or my personal my personal math channel. I will post a thing later. But yeah. Any topic, I mean, any topic, sure. You want to DM me, can also, or like in my channel. DMs, they will easily get lost, but I will try to answer. Any topic, any questions you have, can. Yeah, good luck for O levels tomorrow, guys. Good luck, really, really good luck. All the best.